All right, we've got another exercise on proving that things are Radon measures. So define nu in this way, and then we know, and this is from chapter 2, I think there was some proposition, and this is part D, that integrating a set with respect to a measure or something, or maybe it wasn't chapter 2, I don't know. We know that nu is a measure. We've done this plenty of times before, where we take a measurable function and we define a new measure, an NEW new measure, which in this case happens to be nu NU, such that it's given by integration over a set times phi of d mu, where phi is a mu measurable function. We've done this before. These things are measures. So let's see here. So we're going to prove something stronger than being finite on compact sets. So given any Borel set E, we're going to call this Borel set Bx. Yeah, X is our space. Nu E is equal to the integral of E of phi d mu. Actually, no, let's not even do this. Let's just note that nu of x is equal to the integral over x of phi d mu. And this is finite since phi is in L1 of mu. Thus, nu is finite on all Borel sets. And in particular, on compact sets. So that's stronger than what we need, but this fact will be really useful. Also, since phi is in L1 of mu, the set where phi is positive, phi is a positive function, right? Yeah, the set where phi is strictly positive is sigma finite. And that's because if the set where sigma was positive were not sigma finite, then you could get a contradiction. For example, you could write because you can write phi positive as the union over all n and n of, what is this, of phi inverse of the open interval from n inverse to infinity. And then, yeah, all of these have to be finite. Right, yeah, all of these have to be finite, because otherwise, or actually, this would maybe make more sense if we wrote this phi is greater than 1 over n. Because obviously these all have to be finite, because otherwise phi would have infinite integral. But if these are all finite, then this set is sigma finite. So there you go. So this is sigma finite. So now to prove an irregularity, I don't really want to work with E, so let E tilde, actually no, let's call it E. Let E be open. Yeah, because we want an irregularity on open sets. So let F be E intersected with the set where phi is strictly positive. Then F is a subset of E, and F is, let's see here, it's Borel, because it's intersection of two Borel sets. This is Borel because it's the inverse image of a measurable set, and this is Borel. No, inverse image of a Borel set, and this is Borel. So F is in E, and this, and F is Borel, and what else is F? F is sigma finite. And that's because the set where phi is positive is sigma finite. So now, let epsilon be greater than 0. Since mu is redan, mu is an irregular on sigma finite sets. Now, I'm not going to use this yet, so that this is kind of poor organization, but I mean, I've already written it down. I'm not going to change it now. So, if only this pen came with some erasing mechanism, but it doesn't. So by sigma, here, let me erase this and rewrite it. Sigma finiteness. Let E be the disjoint union from 1 to infinity of En, where each mu of En is finite. And in this statement, I've kind of baked in that all the ENs are measurable. That should be kind of obvious. Like, I'm not going to define a set that's not measurable. So, no. I'm not going to define a set that's not measurable. So, yeah, there we go. This is rel. So now we've got this, and now here we want to apply corollary 3.6 because we've got these like sets here, and we want to approximate them from within by compact sets, but we want to do it like really well. So we have corollary 3.6. What does that tell us? For every single n in n, I'll just write this for all n, we can choose some delta n greater than 0 such that if mu of a measurable set A or Borel set A is less than delta n, then the integral over A of phi d mu is less than 2 to the minus n minus 1 epsilon. And that's corollary 3.6 tells us that given any epsilon, there is a delta such that if the measure of A is less than delta, then the integral over A of a measurable function f d mu, of an L1 function f d mu, is less than epsilon. And so we're doing this, but we're finding deltas for every single n. So now for all n and n, by an irregularity on finite sets. So here is where we're using an irregularity on sigma finite sets, and finite is just like really sigma finite, like completely finite. So for all n, there is a compact set Kn, which is a subset of En, such that the measure of En set minus Kn is less than delta n. And this is why I needed to break up E into the ENs, because if the E had infinite measure, this statement would not make any sense. We couldn't. Sure, we could choose a compact set Kn or a compact set K whose measure was arbitrarily large, but we couldn't get it within epsilon of En. or within epsilon of this set in measure. And that's what we need here. So then what? Then the sum from n equals 1 to infinity of the integral of en set minus kn of phi d mu is less than epsilon over 2. Because each one of these, we chose delta, we chose kn so that this is less than delta, and so that this integral is less than 2 to the minus n minus 1 epsilon. And so we can approximate this by just summing up all these 2 to the minus n minus 1 epsilons, and if you sum them, you get just epsilon over 2. That's why I included this minus 1 here, is to get this epsilon over 2. And that is going to be necessary. Also, there is some n and n large enough such that the sum from n equals capital N plus 1 to infinity of the integral over en. Yeah, that's fine. Of phi d mu is less than epsilon over 2. And why is that? Well, that's because phi is an integrable function, and so its integral is finite. And so because the space x is equal, x contains e, which is just the union of the en's, then the integral over, if you were to sum the integrals over the en's, then you would just, because they're disjoint, you would just get the integral over the union. And that would be finite. And so for this to be finite, it must converge, and for it to converge, its tail must get arbitrarily small. And so then, let's see here. I'm going to scroll down, and I'm going to scroll down like here so that we still have the irregularity part there. Okay, so let k be the union from n equals 1 to capital N of kn then k is a subset of E. Oh wait. No, k is a subset of F. That's, well, yeah. K is a subset of F, which is a subset of E. Oh, wait a minute. Let E be open, let this. By sigma finiteness, let F be the disjoint union of the FNs. This, yeah, that was kind of a mess up. I didn't do this. I didn't introduce the notion of, or the notation of the FNs when I wrote this up. So I got to go back and fix these. But yeah, so we want to work with the FNs because these guys are sigma finite, and so we can kind of, everything works well with them. So k is a subset of F, which is a subset of E. So k is a subset of E. K is compact because it's a finite union of compact sets, and this is why we needed to introduce this capital N. Just doing the sum from n equals 1 to infinity, or just working with these kns would not be good enough. That's why we had to do this 2 to the minus n minus 1, and not just 2 to the minus n and just get the epsilon from here and go from here. Is that we could not take the union of these compact sets and get a compact set. You can imagine scenarios even just on the real line where this would give you just a closed set. So let's see here, k is this, k is compact, and we want nu of k to be big enough, or at least close enough to nu of E in measure. And so let's see here. So what would be the difference between this? Well, this is equal to nu of F. Let's see here, nu of F is equal to the sum of all the FNs. And so if we want to account for k, what we need to do is for the first n terms, we need to subtract fn set minus k phi d mu. Is that right? Yeah, because for these, well, and then we've also got to subtract the sum from, right, yeah, because this is just k, because the k's is just the union of the kn's. And so what you want to do is you want to take the nu of the f, and then from the first n terms, you need to subtract the gap between the fn's and the k's. And then for the rest of the terms, you just need to drop them completely. By the way, for all of this stuff here, the fact that phi is greater than or equal to 0 is really important. So keep that in mind when you're watching or doing these calculations on your own. So then this is greater than or equal to, well, nu f stays the same, and then this minus n equals 1 to n fn phi, we know that that's less than epsilon over 2, so minus that is greater than epsilon over 2, so this is actually greater than, strictly. And then this minus here, using this is also greater than epsilon over 2, so this is just minus epsilon. But f is E intersect where phi is positive, so it doesn't vary from E in measure in any way. So this is just equal to nu of E minus epsilon. Now, such a compact set K exists for all epsilon greater than 0, and thus nu is inner regular on open sets. And there we go with that. Now the last thing we need to do is basically do a very similar argument to this again, but with closed, but with outer regularity on Borel sets. And this ends up being a little tricky. What you want to do is you want to use this compact set argument. So let's give ourselves a bunch of space here. Let's see here. Finally, for outer regularity, let E be just a Borel set. Let F be E complement intersect phi positive. Then F is Borel and sigma finite. Borel since it's an intersection of Borel sets, sigma finite because phi strictly greater than 0 is sigma finite. Now this, we should draw a picture here. I'm very visually oriented, and these help me out a lot. And especially in this part of this proof, it's really helpful. So let's see here. So this is going to be E, and this is going to be E complement. So this whole 2B looking thingy is just going to be X. And so X is broken up into E and E complement. And then this thing on the inside here, this is going to be phi greater than 0. So this region here, phi is identically 0 here, and phi is identically 0 here. And then what is F? F is E complement intersected with this thing. So I'm going to put F down here, but F is like this stuff in here. This is all F. Okay. So now by inner regularity, given epsilon greater than 0, there exists a k subset of E. No. God, I'm mixing up the notation with my notes. K subset of F such that K is compact and nu of K is greater than or equal to nu of F minus epsilon. So this is going to be K in here. And let me see here. So F is E complement, so E is open, so E complement is closed. And then phi strictly greater than 0, that's open. So this is the intersection of a closed and an open set. So this doesn't need to be like anything. So here, let's make this Borel. Because remember we know here, yeah, we should go back up and fix this actually. Because let's see here. So nu is finite on Borel set and irregularity. Let E be. I'm gonna let E be Borel because all of these because Rodin measures are nice on Borel sets. They're irregular on Borel sets. So let F is this, and F is Borel and sigma finite, irregular, blah blah blah. See, all of this stuff here, this all still holds because for all n by inner irregularity on finite sets, that part still holds. That didn't require E to be Borel. It would have, or E to be open. That would have required this would have required the ENs to be, or this would have required the FNs to be open if the FNs were not necessarily sigma finite. But here we constructed the FN specifically to be sigma finite and moreover to be finite. And so that's why this is all fine. And then, yeah, everything else works fine. So we have an irregularity on Borel sets. And so this irregularity argument works because even though F is not open, even though F is not open, it's Borel. Okay, so nu of K is greater than or equal to nu of F minus epsilon. So now let U, right, yeah, so K is compact. So let U be K complement. Then, see here, E is a subset of U, right? Because K is just this little blob here, so U is everything else. So it includes this part of, it includes all of E, and it also includes a lot of E complement. This region here where phi is 0, and also this part of F here where phi is positive, but it's just not in K. But anyways, that's just so that you see it. But what's important is that E is contained in U, then U is open. U is open because compact sets are closed. Wait, we're in a general space here. We don't really know much about X. Compact sets are closed. I'm pretty sure that's always true. I know that's always the case, or yeah, it's always the case that closed subsets of compact sets are compact. But yeah, I'm pretty sure we're fine here saying that compact sets are closed. Although I do forget things here and there about topology from time to time, but yeah. Oh well. So yeah, so K is compact, so it's closed, so its complement is open. And basically this open set is going to be the one that we want for our outer regularity. Because what is its measure? It's, let's see here, by definition, it's nu of K inverse. And nu of K is greater than or equal to nu of F minus epsilon. So nu of K inverse is less than or equal to nu of f complement. Hold on. Right, yeah, okay. Just reconciling the definitions I wrote down with the ones I wrote down on my script versus the ones that I have here. So this is f complement minus epsilon. But if we look at f complement, what does f complement contain? Well, there's this part of e complement here where phi is 0, and so that has no effect on the new measure. The only thing that really comes into play here is this e. So this is equal to measure of e minus epsilon. Oh, but there we go. Such an open set U exists for all epsilon greater than 0. Thus, nu is outer, not onter, but outer, regular on real sets. And hence, nu is Radon. And there we go. With some of these, there's quite a few things that you need to check for something to be a Radon measure, so some of these can be quite lengthy, but a lot of times it's just, some of the stuff is a little counterintuitive, but once you get the hang of the flavor of these types of things, there's a lot of like breaking, just trying to get sigma finite sets, and then if you have a sigma finite set, breaking up into finite sets and just working with those. It tends to be not too bad once you know the flavor of what types of things you have to do. But it is just a little grueling to kind of sit down and do it. But once you do it, you get this. And so we've done the proof.